Welcome to this robotics lectures on basic and advanced concepts. Okay, so this is an NPTEL course on robotics, basic and advanced concepts. In the last lecture, we looked at mobility of parallel manipulators. In this lecture, we look at the inverse kinematics of parallel. Okay, so what is the problem statement in inverse kinematics of parallel manipulators? We are given the geometry and the link parameters and the position and orientation of a chosen output link with respect to a fixed frame. And the problem is to find the joint variables. Now, in this case, we have both actuated and passive joint variables. This problem is simpler than the direct kinematics problem, since no need to worry about multiple loops or loop closure constraint equations. Okay, we will see that we can break up this problem, okay, into serial chains and obtain the joint angles in each chain in parallel. Okay, meaning in parallel means the first chain and the second chain can be computed separately. So if you want to break this parallel manipulator into chains, we have to make sure that no chain is redundant. Okay, remember, in a serial robot, if you have more than 6 joints in 3D space, or if you have more than 3 joints if the motion is planar, the set of equations are redundant. Okay, so we cannot find unique inverse kinematic solutions for a redundant chain. So the worst case in the inverse kinematics of parallel manipulator is the solution of the inverse kinematics of a general 6R serial manipulator. Okay, let's go back to our very simple example of a planar 4-bar mechanism. So we want to find the inverse kinematics of a 4-bar mechanism. Okay, this is in some sense the simplest possible way problem. It's also a little bit cooked up, nevertheless. So we have broken this chain, which is the output link. Okay, we have broken the output link at some point A and B. The coupler is chosen as the output link. And we are given the position vector of a point on the coupler link and the orientation of the coupler link, okay, with respect to, let's say, the L, which is the fixed left-hand side coordinate system, or the right-hand side coordinate system. Okay, so what do we have? So we have broken it at this place as shown in this figure. We have A, okay, which is at the point of breaking in the coupler link, and from this side it is B. So we are given X, Y, and this angle phi, which is the orientation of this coupler link. And what do we have to find out? Theta 1 and phi 2. What else is given? L1 is given. Okay, all the geometry is given, L1, L0, L3, and this A and B, which together add up to L2, is given. So to reiterate, we are given the position of the point LP and the rotation matrix L2R of the coupler link. Okay, so this is a planar case. X and Y coordinates are given, and the orientation angle phi is given. The link lengths L0, L1, L2, which is A plus B, and L3 are known. So how do we solve this problem? It's very simple. We look at X and Y, which is L1 cos theta 1 plus A cos theta 1 plus phi 2. Okay, standard 2R planar manipulator. And Y is L1 sin theta 1, A sin theta 1 plus phi 2. Okay, so X and Y are known. So the angle phi denoted the orientation of link 2 is also given. So we can solve theta 1 and phi 2 from these two equations very simply. Okay, two equations in two unknowns. X is given, Y is given, theta 1 and phi 2 are the unknowns. So we have done this in the lectures long time back when we looked at capital X, capital Y at some point on the planar 3R, and then we did some square and adding, and then we did some manipulation to show what is theta 1 and phi 2. Okay, so theta 1 is nothing but A tan 2 Y minus A sin phi, X minus A cos phi. So if you X minus theta 1 plus phi 2 is phi plus 2 pi, and if you substitute back, you will get X minus A sin phi and X minus A cos phi and Y minus A sin phi. We can do the A tan 2 of that and we get theta 1. And phi 2 is nothing but phi minus theta 1. Okay, we can ignore this 2 pi business. In a similar manner, if we consider the other side, okay, we can show x is L0 plus L3 cos phi and b cos phi 1 plus phi 3, and y is L3 sin phi and b sin phi 1 plus phi 3, and phi is phi 1 plus phi 3 minus phi. So x, y, and phi is given. So what do we have to solve for? We have to solve for phi 1 and phi 3. Again, phi 1 obtained as theta 1 plus phi 2 minus 2 pi, and phi 1 plus phi 3 minus pi must be same. Okay, if you think about it, whether you obtain from this side or from the other side, both must be same. The 4-bar mechanism is a 1 degree of freedom mechanism, and only one x, y, or phi can be independent. Okay, so we need to make sure that the x and y are related through the 6-degree coupler curve, and phi must satisfy x cos phi plus y sin phi is given by this. Okay, so the constraints on the position and orientation of the chosen output link x, y, phi are analogous to the case of the inverse kinematics of serial manipulators where n is less than 6. So if you go back and remember, in the SCARA case, the motion was in 3D space. However, the two angles of the end effector about x and y, they were 0. Only the z was allowed. So in this case, this x, y, and phi, which you give me of a point on the coupler, they must satisfy the 6-degree coupler curve and also this equation. Okay, otherwise it is not a consistent problem. We cannot solve an inverse kinematics of a point which is not on the coupler curve. Okay. So the inverse kinematics of a 4-bar mechanism can be solved when the given position and orientation is consistent. Let's look at a 6-degree of freedom parallel manipulator. So in this case, we have looked at this 3-fingered hand gripping an object. So I am showing one finger as an R, 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 S chain. Okay, so the other 2 fingers are not shown. So what is given? The position and orientation of the gripped object. Okay, so this is the object which is gripped. So we are given some point on the gripped object. So as we were looking at the centroid of the triangle formed by this, and the x, y, and z, x was along S1 to S2, z was perpendicular to this, and so on. So the normal to the plane. So the orientation of this plane and the centroid of this triangle is given to you. So what do we need to find out? We have to find out the angles theta 1, psi 1, and phi 1. Likewise, we have to find out theta 2, psi 2, and phi 2, and theta 3, psi 3, and phi 3. We need to find out all the joint angles. So how do we do this? It is not very hard because we have just the position vector of a point which is, let's say, the centroid of the gripped object. The rotation matrix of the object with respect to base is also given. So we can find out that the xyz, okay, of the point is given by base S1, which is the corner point where it is gripped. That is nothing but base to object, object to S1. Okay, so we are going to the centroid and coming back, and this will be equal to base to P object. Okay, so if you go back and see the figure, so this point xyz is nothing but a vector from here to here and from here to here, and then that should be equal to this vector. Okay, so I want to find out the position vector of each one of the spherical joints from the given data, which is very simple. We come to the given point of the centroid and then go back to this spherical joint, which is exactly what is done here. And it turns out that the xyz is related to cos theta 1, okay, then L11, L12, L13, and the angles cos psi 1 x coordinate and cos psi 1 plus phi 1. The y coordinate is related to the sine of these angles, sine theta 1, and then cos psi 1 and cos psi plus 1 plus phi 1. And the z coordinate is related to sine psi 1 and sine psi 1 plus phi 1. Okay, and then this d and h, so d is the distance between the two index finger and the middle finger, and h is the distance along the vertical. So these are 3 equations in 3 unknowns. xyz is known. xyz is known from the location of the object, centroid of the object, and from the centroid to that point, okay, which is given. And then we can find out x theta 1, psi1 and phi1 from these three equations. Okay, it's very easy. We can eliminate one at a time and obtain. So for example, if you do this operation, x squared plus y plus d whole square plus z minus h whole square, we will see that we will get one equation in L11 square, L12 square, L13 square, and cos psi1 and cos psi1 plus phi1. Okay. The last z component of this equation does not contain theta 1. It contains only psi 1 and psi 1 plus phi 1. So we got one equation in psi 1 and psi 1 plus phi 1 from this three of them, and one which is the z component. Okay. So we have two equations. Okay. The last equation can be written only in terms of psi 1 and phi 1. So we have two equations in phi 1, psi 1, okay, and they can be written in this form. So a1 cos psi 1 plus b1 sin psi 1 equal to plus c1 equal to 0, and similarly I equals 2. And we can compute a1, b1, c1, a2, b2, c2. So they will be all functions of only phi 1 because the psi 1 is taken out here. The usual trick when we learned how to do elimination of one variable from two equations. Okay, and then we use the Sylvester's dialectic method. We eliminate psi 1 and we find out the determinant of Sylvester's matrix equal to 0. So in this case, that will lead to this equation, one single equation in phi 1, okay, equal to all these constants. So C1, L1, Z, H, all this will show up. Okay, so it's a single equation in cosine phi 1, and we can go back and substitute the tangent half angle for cos phi 1 and sin phi 1, okay, and we will get a quartic equation. Okay. So remember, C1 also had sin phi 1, cosine phi 1. Okay, so it looks like that there is only cosine phi 1 here, but there is a cosine phi 1 square here. Okay. When you do tangent half angle substitution, cosine phi 1 will become 1 minus x squared divided by 1 plus x squared. So square of that will give you a fourth degree or a quartic equation in tan phi 1 by 2. Okay, so you can solve this from the phi 1 from this quartic, and then in the process we obtain also psi 1. This is the standard elimination technique. Okay, so when we write a0 y plus x squared and so on, when we've obtained y, we also obtain x in the quadratic or in the quartic. So phi 1 can be obtained by solution of this quartic equation, and psi 1 can be obtained by simply 2 tan inverse of a1 c2 minus a2 c1 and so on, okay, divided by b1 c2 minus b2 c1 plus a1 b2 minus a2 b1. Okay, so these contain phi. So, and finally, theta 1 can be obtained by a tan 2 of y plus d comma x. Very simple, because y. So theta 1 contains here something here and only one theta. So x and y will contain theta 1. So if you take d on that side, and then you can manipulate very simply because the quantity in the bracket are same in both of them. Okay, so we will get some a tan 2 of y plus d comma x, which is what is written here. Okay, so the joint variable for the other two fingers can be obtained in exactly the same way in parallel. Okay, so we solved for the three angles in one finger, the other three angles in the other finger, and the third three angles in the third finger can be obtained in exactly the same way. Let's look at this inverse kinematics of the Stewart-Gough platform. This is a very famous platform, 6 degree of freedom Stewart platform. So what do we have here? We are looking at one leg of the Stewart-Gough platform. So there is a fixed coordinate system B0. There is a coordinate system which is attached to the top platform, which is given by P0. The point platform, which is an S joint, is located by this vector P0 Pi. A point on the base where there is a U joint is located by this vector B0 Bi. Okay, so what you can see is this vector from fixed base to this point, which is B0 Pi, is nothing but B0 P0 Pi, which is this vector, pre-multiplied by a rotation matrix, which gives the rotation of the tap platform with respect to the base, plus this vector B0T. So this plus this will be given by this. Okay, this is known. And this is also given to us in the inverse kinematics problem. We are given the position and orientation of the top platform. Okay. So hence, from this, the location of all these P0 Pi, P0 Pi, everything is known. So this point is known, basically. Okay. So the location of the spherical joint can be obtained in the fixed coordinate system. Now, as we'll see, this location of the spherical joint can also be written as a vector from the fixed coordinate system to the U joint, which is B0 Bi, plus a vector in the leg, okay, which will be like Li along some direction. Okay, so that is what is given here. So this XYZ, which we obtained from the coordinate of the S joint, minus B0 Bi, okay, minus B0 Bi will give a vector along this length. Okay, so that is what is given as some rotation matrix, because we need to multiply this vector. Okay, and this is given as first one rotation about at the U joint, another rotation at the U joint, and a translation along the length. Okay, so let's go over it once more. So this vector here can be written as this vector minus this vector. So we know this vector from this argument, that position and orientation of the moving plate is known. So from this vector, if you subtract this fixed vector, we'll get a vector along this. Now this vector is basically due to rotations, two rotations at the U joint and one translation. Okay, so that is what is written here. If you multiply out these two rotation matrices, one about y by phi, x by psi, and then this translation, you will get L1. The x coordinate is sine phi 1 cos psi 1 minus L sine 1 and cos psi 1. Okay, the left hand side is known because we know x, y, z, we know the location of the U joint in the fixed base, and we know how to rotate this to obtain the correct direction. Okay, so we have three nonlinear equations. Left hand side is equal to 3 and 1 length, which is we don't know, and two angles, phi and psi. So three equations in three unknowns which can be solved. Okay, it turns out L1 is nothing but plus minus xyz minus b0 bi whole square. So the length along the translation along the prismatic joint is nothing but the location of the spherical joint minus the location of the fixed base and the magnitude of that. Psi 1 can be obtained as a tan 2 minus y plus minus x square plus z square. Okay, and phi 1 is a tan 2 x by cos psi 1 z by cos psi 1. Okay, so and what is x, y, z? They are nothing but the components of the left hand side. So x, y, z are the components of this rotation matrix into this. Okay, and we can do this for each leg. There are 6 legs in the Stewart platform, and we can find out the translation at the prismatic joint and the rotations at the U joint, at the hook joint at the base. Okay. So in summary, the inverse kinematic involves obtaining actuated joint variables given chosen end effector position and orientation. Again, the key concept is to break the parallel manipulator into simple serial chains. The inverse kinematics problem can be solved by considering each serial chain in parallel. So we solve each of them separately and independently. That is what is meant by parallel. Okay, this is also one of the reasons why these things are called parallel manipulators, because we can solve the inverse kinematics in parallel. So the inverse kinematics of a Stewart-Gough platform is much simpler than the direct kinematics. In the next lecture, we'll look at the direct kinematics of the Stewart-Gough platform. Okay, this is one of the hardest problem to solve. In general, inverse kinematics problem simpler for parallel manipulators. Okay, in the serial manipulators, the direct kinematics was very simple. Inverse kinematics were harder. In the case of parallel manipulators, the direct kinematics is much harder and the inverse kinematics is simple. So with this, we come to the end of this lecture. And the next lecture, we'll look at the direct kinematics of the Stewart platform manipulator.